Hi, everyone. My name is Rob Jacob, and I'm going to talk about the progress in the infrastructure group since the fall meeting and our future issues. And I'm speaking on behalf of my co-lead, Shaocheng, and the entire infrastructure group. So in case there's some new people on the project, the infrastructure group responsibilities are to develop, maintain, and support software that is needed for E3SM, but not part of the main prognostic models. So that includes the configure, build, and test, diagnostics and analysis tools, workflow, and the driver and coupler. We also manage the input and output data sets, and we define and document and manage the processes and procedures used in software development within E3SM. Basically, everything we do should help make the model development, simulation, and analysis happen and be easy. So starting off with some big pictures view of the main model development, we are still averaging about one PR merged per calendar day. Of course, a lot of that is because if you want to change a compiler option or something about the machine configuration that requires a PR. The V2 water cycle developments have been mostly done, but we said that in October. And one of the things that the infrastructure group has done is we've added more metadata to all of the main models, atmosphere, land, river model, and all ocean and sea ice. And this includes global metadata and also standard names for each variable for the popular CMIP variables and corrected units where we could. And then we've made several tags to the main model source code in order to capture V2 development. Starting with V2 alpha way back in September of 2019, going through the Club Odyssey in April and July last year. In December last year, we made Theta L the default die core. Then there's been a lot of focus on the ocean and its heat and its circulation, including a lot of interaction between the ocean and sea ice involving frazzle had to be worked on. And but we are, I believe, pretty close to a final version. This chart over here shows commits per week, I think. This line here is 150 in case you can't hear it. See it? Of course, a pull request can have several commits in it, so this is a larger number than the number of pull requests made. We've made some changes to the submodules and code structure, particularly in SEAM. We now have our own copies of the coupler, the data models, and the share code. So all of these paths have the code in them has now been moved to different locations, including most recently the share code, which is a collection of Fortran utilities needed by two or more models, usually atmosphere, land, and data models. And the seam paths, these paths are still there, but the build ignores them, and you should ignore them too. Basically, if you're familiar with SEAM, SEAM refers to several things. There's the case control system, there's some standalone Fortran tools, and then there was all this Fortran and C parts that we used to share, and we are now basically CESM and E3SM are getting our own versions because we realized that we just couldn't maintain a single source copy of these for our different science goals. And then another change to the code structure is MPass framework is no longer a submodule. It's now included directly into the repository. So before the V20 tag, we're going to have to update some READMEs and some other docs. And then master will start receiving any remaining BGC and Cryosphere V2 pull requests. For example, GCAM is going to be added to the model and Marble. And we'll also start accepting answer changing developments to existing components. So the development timeline, if each dot is like a merged pull request onto master, we're somewhere around here. There's a V2 RC4 tag that we'll probably make, and there won't be any changes to answers at all after this. Here we might be adding some readmes and other documentation. And then we'll make the v20 tag. And then master will still be in like a v20 state until the point where we're ready to commit something that changes the v2 water cycle answers. And then before that happens, we will make a branch, maintenance branch for version 2.0. And somewhere after this, we expect the 2.1 alpha tags to start being made for the BGC v2 experiments. So some of the recent and upcoming changes to the testing, we're using the Circle CI service to test every PR automatically using cloud services and the GNU compiler. It just tests the build, actually. It doesn't do a run because the free service isn't quite beefy enough to do a run. This replaces Travis CI, which went away from a free model. We removed one of the Sandia machines, Sandia TOS 3, from our integration testing. This Sandia TOS 3 did a great job, and its predecessor machine did a great job doing our testing for our integration case since the project started, really. But there was always this issue of it was hard for anyone not at Sandia to get on the machine to debug any problems. So it's been replaced by Chrysalis, which now does our nightly testing of E3SM integration with baselines on both Next and Master. Coming soon, we're going to start testing on this small machine called Ascent at Oak Ridge, which is a small version of Summit. So it allows us to run our test suite on the same hardware and the same software stack. We're going to add a maintenance 1.2 test suite. And we still need to go through and convert our developer integration and production testing to using v2 configs. Things like FizzGrid. We're still not really using FizzGrid in most of our tests. We want to replace the new thermodynamic capability of MPass C-ICE for C-ICE in the F cases that we run in our tests. We need to add some more tri-grid configs because that will definitely be what BGC is using, and will I assume be the future for version 3. We have a low res tri-grid capability that uses a 2-degree river model grid. So the land and river will be on a 2-degree grid, but so far this isn't yet working within the land model itself. Still waiting on that. A Chrysalis update. After a rocky start, Chrysalis is now our fastest machine, and we love it. We're getting 40 years a day for the V2 low res configuration and 10 years a day for the regionally refined model configuration. Chrysalis is 512 nodes, each with two 32-core AMD EPYC CPUs and 256 gigabytes of RAM. We have 3 petabytes of disk. And basically what happens is after installation, we found and fixed several issues. We had to turn off our resource hogging GPFS monitor. We had to switch to the network specific OpenMPI, but only after finding and fixing a bug in that MPI stack. And we also done some firmware updates, changed the topology, turned on simultaneous multi-threading. And this was all work done by Oz and Jayesh and people at Argonne and LCRC. So we're now very happy with this machine. Other developments in the infrastructure group, the Moab-based coupler and related tools are continuing to progress. We can now build Moab instances and meshes on all of the major models. We can create all of the major maps online while the model's running. We can read the pre-computed maps that we have to read in parallel. We can create load balanced and geographically compatible decompositions. There'll be more on that later in Andy's talk. We still need to implement the full coupler data flow and services like merging and some of the flux calculations. The MB Tempest tool that we make available for calculating maps in parallel using the Tempest algorithms has been updated on all platforms. We found a new method for finding matrix weights in some degenerate cases. We fixed a bug in the SE to FV case, which was preventing us from making good maps in the Hydra 1K to NE 1024 case, which we can now do in about 10 minutes in parallel. And this is capability is being added to NC Remap for those of you familiar with that interface. So the data archiving and publication that we do, we've added more data sets. It's doubled just in the past year. We have about 596 terabytes of data that are in the kind of the native or near native E3SM format, and then another 12 terabytes in the CMIP6 format. The archive at Livermore has raw data for every simulation online on spinning disk. We've recently publicized a Cryosphere V1 and a 21-year high-res V1, BGC and COVID NIP sims. We've been working on validating and validation tools and other tools to help with the workflow of getting data from a long-term archive and into ESGF. There's actually a lot of steps involved. We've also been assisting on CMIP publication for some of the external projects. We're planning to publish some more output in CMIP format, some monthly variables and some additional monthly variables. There's also a new ESGF node at Argonne, which is ready to publish some data sets. So we'll have 2 places we can go to, including backup. So as mentioned, the infrastructure group works on a lot of the software that kind of surrounds the model. And this is a schematic of the workflow that you might do in climate modeling. You'll configure the model, you'll build it, you'll submit it and run it. You'll then might short-term archive some of the results. And then from the archive, you might need to put stuff on tape. You might do some diagnostics and analysis, and you might want to publish. And we work on tools for all of these stages. So in the past, since our last meeting, our last all-hands meeting, there's been a lot of development. In the case control system and the run script, there's a shorter version of the run E3SM script available. It still does a lot of the things that you're used to if you use the script, but it's now much easier to understand and modify. The create new case command, which is called by run E3SM, has a new optional argument called case group, which we would like to see used to indicate that a case is part of a larger group of simulations, and that can then be used in our provenance collection to make sure those cases get grouped together properly. Some of the more specific things we've done to enhance provenance collection is there's a new case hash that is created. This is not the Git hash. This is a hash associated with the case creation. And that will help us also to delineate cases that are submitted to our performance archive and other provenance collection services. Because the case name itself is not guaranteed to be unique, but the hash will be. There's more info on the status of the Git repository when you run the code that is collected, submodule status and any code diffs. We have this replay.sh file that gets created for you as you create and modify a case within SEAM, which then has all the commands you need to reproduce that configuration. And we also capture the run script if you're using it as part of the provenance. And performance tracking has also been boosted. We now include detailed I/O timers from Scorpio, and there's also more memory use reporting. So the analysis and diagnostic tools that we develop in whole or in part include NCO for command line regridding and climatology generation, and E3SM diags, which has been mostly used for the atmosphere, but we're now extending it to the land and river. MPAS analysis, diags for ocean and sea ice. ZStash is our tool for taking simulation results, tying them up, and putting them on tape. E3SM to CMIP is a workflow tool for converting output to CMIP format. E3SM Unified is our content package where we put all of this together into one easy to install package. And Zippy is a new tool that you're going to hear more about soon for doing parts of the post-processing tool chain automatically. And we are connecting a lot of things in the in the BER or system model development universe to our analysis and diagnostic tools. So we're going to release, make a release of E3SM Unified in July. We're trying to do these, I think, twice a year. It's available on all of our platforms. There's a simple command you execute to put all these tools into your path. We maintain actually the conduct package on these platforms. You just have to execute this a single line to get them all in your path. We're going to do things like updating E3SM diags to include tropical cyclone analysis. MPath analysis will include some performance and config improvements. NCO is going to include its support for Entity Climo monthly operations and better supports for MAST. Zstash is going to support the tar file-based checksums. E3SM to CMIP has supports for high-frequency variables. We'll have this new debut of our Zippy package. It will also include the Tempest Extremes, which does things like hurricane tracking and other feature tracking. So you may have heard about Zippy. A little bit about it. It's our tool for automating most of the post-processing workflow that a scientist will do once they have their data. The goal is to speed up the post-processing by allowing some automation of these tasks and also serve as a standard tool so that everything is done consistently. So it'll do things like basically you have a configuration file where you specify what kind of analysis you want to do. Zippy will then generate the jobs that have to actually be done to make that analysis happen, and launch several jobs, including with figuring out the dependencies to onto your whatever compute platform you're using to make them all happen. We're going to have documentation and tutorials on how to use this once the 1.0 version is finalized. So going forward, we're going to keep integrating analysis and priority metrics that come to us from the science groups, support new tool development as we see necessary, and Zippy has grown out of that need. Set up and document the best practices for running the model and post-processing data. Work with the performance team to interface Zippy and PACE for simulation documentation, automation, and provenance collection and make it uniform. We're going to continue to leverage other DOE-funded projects and make sure that the diagnostics that they provide are available to E3SM users. We've also been working on finding a replacement for some key parts of CDAT that are necessary to a lot of our tools, given that CDAT doesn't have a very clear future. We're working on multi-node task parallelism in all these tools, and increasing our support for external projects that want to use them by providing more documentation and tutorials and Slack channels. So one of the things that we would like to work on in the very near future is encouraging V2 simulation campaign standards. We noticed that the V1 campaigns had a lot of variability in how they were run, and this created a lot of problems downstream when trying to do some kind of uniform post-processing on all of that output. Simulation campaigns run by other groups outside of the project had similar easily avoidable problems. So to avoid this, we're hoping that V2 campaigns will all follow the same process and procedures. Things like naming the cases consistently, and everyone recovers from errors and restarts the same way. And we archive results always with the same process. We're thinking that we can start all campaigns by filling out a campaign planning table, which would have things like the case and the case ID, this new case group, who's doing the run, what machine is it on, and some things you would fill out right after the run starts. And this would be kind of a single place everyone could go to see how the V2 simulations are going and what we are planning to do. And we can also check things like the case name and the case ID to see if they are being consistent. So this procedure has been prototyped by the water cycle group. They have the simplified run E3SM script that gets used to do all the configuration and checkout of the code, the compile, and the actual simulation. Store the results on disk with the short-term archiver and scene, post-process with this new Zippy tool, archive it with Zstash, and then create a simulation page document, which still will be done by hand, but we are going to, as mentioned, work on getting that automated. And Ryan has put together a detailed running E3SM step-by-step guide to help write all this down. And I believe that's all I have. Nope. One last slide on some of our additional challenges we're looking at. So disk management, especially on Compi, is becoming an issue. We are getting a scrubber installed, and we're encouraging people to move files off of there to NERSC as much as they can, and to use the CFS disk on NERSC for analyzing data. For Chrysalis, we're telling people to leave the data there because we can publish and archive locally. There is now a tape system available to us at Chrysalis. Some other data issues we're thinking about is where can we use data compression? Could we use it to output more and higher frequency data that you normally wouldn't do? Can we losslessly compress everything to save more disk space and even space on tape? We also need to keep looking at reducing output in the H0 file, especially for large ensembles. And we want to begin an effort to define and implement metadata requirements for all of our input and analysis data. And for tool use, we're going to keep training and encouraging all the production run managers to use RunScript and Zstash. We want to get all the ecosystem projects outside of the main project using Zstash as well. That's really important, especially when they then come around and ask us to publish the data. And then automatic addition of provenance as runs are processed. Things like the case hash and the case group are all going to help with that, so that we'll be able to go to a website and browse really deeply into not just performance data, but analysis figures and all kinds of metadata about our simulations. Okay, I think that's it. I will take a look at the chat to see if there's any questions.
No, but they seem to have all generated answers for themselves, so I don't see anything new there except the possibility of new one. What is the status of Adios in the post-processing? Is it ready? From Charlie Zender.
Oh, so that would be the automatic conversion of we do have the ability to automatically convert Adios to NetCDF before the run ends. So that should interface smoothly with the post-processing tools rather than trying to read Adios directly. We're not gonna try to do that. And we just haven't had an occasion to use Adios in production. I know that Screen wants to use it, I believe, for their next diamond simulation, but the V2 sims can continue to use NetCDF directly.
Okay, Peter Caldwell, I missed you because I got caught up in the exchange over the PIO files. Anyway.
Yeah, I just wanted to ask what specifically you meant by recover from errors and restart in the same way when you're talking about V2 campaign standards?
It means when the model fails in the middle of a run, what we noticed was sometimes some of the history files, if you didn't clean them up correctly, would have extra data or somehow get corrupted, and then those bad history files would get Zstashed and everything else. And so we want to make sure that when your model bombs for whatever reason in the middle of the run, this is how you back up and restart.
And so is there somewhere that I could look that would explain to me what the best practices for doing that is, or does that still need to be created?
It needs to be created.
Okay.
Okay, just, yeah, the other things I think are self-explanatory. Aaron, just, you want to explain what you started here? And why?
It was an innocent question. So I don't know if it's that intense, but I just noticed that some of my E3SM run directories would be sort of populated with a ton of PIO logs. And actually, I wonder if it's built into PIO because some of my screen runs that use PIO, and those are just like not even using Seam. Sort of standalone runs will have these PIO logs, and you get so many of them that then when you're trying to look at what's in the directory, you just see a bunch of PIO logs. So I was just curious if we could turn them off. Or I guess, and then Matt suggested that maybe we could just put them in a separate directory in the run directory, and then it just wouldn't just sort of populate the directory with a ton of files.
So yeah, so file clutter is your real problem, which is an issue, right? So
Yeah.
Right. Yeah.
particularly
Exactly.
since we use file names for metadata tags in cases like that, and you want to get rid of things you don't need. So, okay.
Mark was asking about the Adios to NetCDF post-processing tool. It is, I believe, called by Adios itself. So it's not something I can't remember actually. Jayesh?
Yeah, so the post-processing tool that is used to convert audios files in the CDF is available and it works fine. We routinely use it for our tests. So there are two options for testing E3SM. What we try to do is do the conversion when the file is closed automatically, but that's not what you typically want to do. You want to do the conversion from Adios to NetCDF as a post-processing step. So the tool works right now offline. You have to run it offline. And we are working on integrating that into Seam so that it runs as a post-processing job.
Okay. The automatic conversion when a file closed, does PIO do that or Adios do?
So Scorpio calls this the required API to do the conversion.
Okay. And then I think Andy asked, that was answered. And best developers
Yeah,
are.
about the repo. Pat Worley.
I think
I
Pat's
was just adding to the discussion of PIO logs. So there's pretty much like timing files in many ways. So a subdirectory would be easily implemented and they're already being tarred up and saved as individual files. Putting them in a directory might actually be more convenient all around.
When Sarah jumped in, would this affect, are the PIO files used by PACE?
It would.
Yeah, so actually I thought we already do this. So we already do this so I will double check how file clutter is happening because I thought we were doing the case directory capture and tarring them up. So I will check.
They are tarred up. They are tarred up, but they're tarred up as files in the top directory. They're not put in the subdirectory before they're tarred up.
Oh, okay. Maybe yeah, we can make that change. Yeah.
Okay.
Yeah, my preference is they should be turned on, and we should avoid the clutter too. So because they are not expensive, and we would like them always on, if possible.
If they're just cluttering up the run directory, we'll just move them to a subdirectory.
Yeah, that seems like a good solution.
Okay. Let's move on to the next talk. Luke Van Roekel will talk about the brand spanking new NGD Ocean.
All right, good morning all. And I'm going to talk about the new NGD, which is a improvement to the ocean physics, the discretizations, and the readiness for exascale. So with these massive reorganizations and changes, we have introduced a new name for the component, Ocean Model in E3SM for Global Applications, or Omega. And I will be talking on the behalf of a whole bunch of people Hopefully I mentioned everyone here. Sorry if I missed you. So the history and purpose of this NGD was grown out of the mini NGD started in phase 2, which was to implement WaveWatch 3, and we have just incorporated this into the Ocean NGD code now. So the WaveWatch 3 is ready to run in a few configurations within E3SM. Goals of the new NGD, in my mind, is to firmly establish DOE as the leader in coastal and ocean modeling and coastal ocean impacts, and to accelerate exascale readiness, also to pursue some low-hanging fruit to improve ocean ice fidelity. So I've organized this under a few subgroup areas. We're going to look at the physics, improving the mesoscale eddies, implementing some mesoscale eddies, and improving the vertical mixing. We'll do a bunch of work with the framework, including much increased testing and improved testing infrastructure, and also look at the basic discretization of the code itself. We'll continue pushing on the waves with the main goal making the wave model possible for climate scale simulations and for ensembles. And we're also going to be pursuing a few ML AI ideas along the way. So why start with waves? Wind generated waves are really important to the climate system at the interface of the atmosphere and ocean. Just a few things that this could be responsible for are vertical mixing. You can see pictures from the Deepwater Horizon oil spill forever ago where you see wave-induced convergence of oil. You also have changes to the atmosphere-ocean fluxes due to waves that are not considered now and have been shown to be pretty important in regional simulations. You can change the albedo of the ocean, and you also have some important sea ice ocean interactions. So the wave component is a logical place to start advancing the ocean atmosphere interface and the ocean component itself. So what could we do with this? I like to think of what science can we enable with new capabilities from this NGD. So one of them is the sea state dependent flux, where currently now we have some drag coefficient times some difference in properties. And that drag coefficient is often dependent on low level stability and things like wind speed, but not on the wave state itself. So there have been a few cases out there in the literature for some regional domains, such as on the right here, where we can look at what if we just have a standard bulk aerodynamic flux implementation, and what if we allow the wave state to influence the flux of momentum and temperature between the ocean and atmosphere. You can see there are some very large regional differences due to waves, especially along the coast. Also, the NGD is going to target some of these eddy processes, and what that might enable is interaction with BGC. This is a really nice MODIS image of Baltic Sea chlorophyll, where you can see eddies of various sizes, filamentary behavior, things that will be targeted through a number of things in the NGD. We'll also be looking at the Arctic a little bit in partnership with Interface, the new BER project, where Interface is looking at Arctic sea ice interactions, and ICOM is bringing a tide models. So if we put all of this together, we can start to better simulate sea ice distributions through the Arctic and understand pattern of sea ice loss and concomitant, I think is the right word, impacts on CONUS from this sea ice. I can't go through. There we go. As we get to more of the performant aspects of the NGD, some of the exascale parts, we can actually start to consider regional patches of very high resolution ocean down to the kilometer scale and below, where from ICOM we are targeting getting spatially variable time stepping, which is work ongoing at LANL, that will allow us to have very high resolution domains, but not require time steps consistent with that smallest grid cell through the global ocean. So that could allow us to do things like directly understand the impact of submesoscales on, say, iron production, which is the case here. This was a small regional case in the Southern Ocean, and this could carry over to any other region. And what is exciting about this, it really pushes forward in a unique way E3SM's already unique capability in regionally resolved modeling. So where are we at now? So on the wave front, Stephen Bruce has made really excellent progress on a number of fronts. We have implemented an unstructured mesh within the WaveWatch code, so we can do things like increase resolution along the coast, say over the shelf break. And what he has shown in a paper that's published now in GMD is that you do get the accuracy of the high resolution relative to a global high resolution simulation at a fraction of the cost. And when you're outside of this region, it behaves like the low res. So it seems to be working really nicely. Recently, he's implemented a rotated pole. So now we can do Arctic simulations, and we're getting close to having some connections into the ocean model through Langmuir turbulence. So we're passing the Stokes drift, and that's in progress. On the physics front, sorry about this, a slide issue. We've been working on new configurations. This version, I forgot the image. An idealized configuration in conjunction with the climate process team on eddy energetics. And we've started conducting high resolution, the RRS 18-6 G case as a baseline to understand what the circulation looks like when the mesoscale eddies are resolved. On the submesoscale front, we're working on configuring regional simulations with a large eddy simulation code to understand the instabilities in the mix layer, these submesoscale eddies. So these simulations look a little bit like the movie in the bottom right. On the vertical mixing front, our initial implementation of a assumed distribution closure, which has some similarities to Club, is nearly complete. And we have some nice results on the buoyant convection front. Here we show the LES here in black, and various resolutions of this closure, this ADC model in the different symbols. And what you see that's quite nice here is we are pretty insensitive to the resolution across different heat fluxes, which is not true of the current mixing scheme within MPAS Ocean. Andrew Bradley, Kat Smith have been working very hard on this passive tracer supercycling. It's essentially complete now with some really nice results. Now that we're getting close to where Matt can start devoting to Marvel, they need to make a few changes to variables before it's ready for BGC v2. But the results here show, if you just look at the red bars here, which is the tracer timer from a run, you see it's basically almost cut in half between the two. And so it's a really, really great addition. And this plot on the right shows that with supercycling, we still conserve carbon. So it is working. Zyler S.A. Davis has been doing really nice work on the testing front. He has been working on Compass package, which is configuration of MPAS setups. It's recently gone to a Python package. It has a number of test cases that includes regression testing. We're also moving toward making the process to generate meshes and initial conditions for E3SM more robust instead of relying on codes on people's machines or codes that only a few people know how to run. And it's working right now for MPAS Ocean and the land ice, and we'll be moving this to Omega soon. As you can see, I believe this is a number of changes recently. So Zyler's been making a lot of changes recently to improve flexibility, make it easier to use. Like I said, it's moved to Python and really made some really great documentation for this as well. Darren and Guerta, Sarah Calandrini, and Mark Peterson have been looking at the MPAS discretization in some idealized test cases. This is just one of them. And what they found in this test case, the blue line here, the standard TRISC, so this is the current implementation with MPAS, actually diverges in the L infinity norm. So as resolution goes down, And we also see in a variable resolution case, the standard case has all of this sort of star pattern noise that happens. And so they've been looking at new ways to discretize certain operators, and what they're calling this TRISC CV or TRISC++. They've used changes to the kinetic energy calculation. And when they do that, we go from this solid blue to the red. So it's a really great improvement, and also gets rid of the noise. But there are still remaining questions on this front. They need to look at what changes like this do to the mimetic properties of the standard discretization. So where do we go next? On the wave front, like I mentioned, we're working on Stokes drift and Langmuir turbulence with these new rotated pole capabilities. We are working on looking at how CO2 fluxes might change in the Arctic as the climate changes, as a first low-hanging fruit to show off the capability. This summer, we're also working on the implementation. We have a summer student, Stephen Bruce, and I working on porting the wave source terms to GPU. For vertical mixing, we're getting close to running this new closure in a global configuration. We're also going to be working with partners in interface on simulations of the Arctic halocline, and in particular, a new way to do entrainment into the boundary layer, which has been shown in a number of places to be critical for Arctic simulations. For the mesoscale eddies, we're working toward implementing an eddy kinetic energy-based scheme, which is sort of the state of the science from the CPT eddy energy group. We're also going to work on where high resolution is necessary by doing a series of simulations with targeted regional refinements, and hopefully discover something about AMOC in the process as our targeted physical process. On the sub-mesoscale eddy side, we'll be conducting parameter sensitive sweeps to understand sub-mesoscale closure better, and we'll also be investigating how we can use artificial intelligence, neural nets, to better constrain portions of state of the science parameterizations. So the framework front, we're moving toward a new framework that emphasizes performance, whereas the current framework really emphasizes flexibility. See if we can find something that's a nice middle ground. It will likely port to C++. What I've seen with Phil, when we've talked, we're still thinking about the actual API for this. Throughout the NGD, what my goal is to emphasize a tight coupling between the domain and computational scientists. This includes trying to understand coding standards, not having to write code and then rewrite code to get it onto the GPU. So working together the whole time and transferring knowledge between domains. We'll continue working on increased testing, including more operator convergence. Currently, we only have horizontal advection. We're working on vertical advection now, and we'll extend to vertical mix as well soon. We'll have more unit testing and validation. We're still working on the actual core for this, but it's likely the new core will be built upon Hume-Kang's semi-implicit solver, but also want to explore new time stepping methods, including possibility of IMEX methods as well. And then Darren and Gordon and colleagues are continuing their work on TRISC++. There have been some reports within the community that there are some instabilities out there that they want to investigate. On the Compass front, we're porting more test cases. We're developing new tests along the way as well that I've mentioned, and this summer, Xyler has a student to help work on the task parallelism using Parcel. So that will make the testing more efficient. With Chad Sockwell at Sandia, we're going to be working on an initialization idea. Whenever we initialize large ensembles, say for decadal prediction, often it's done through hindcasts. And anytime that happens, you have these large drifts that quickly approach an uninitialized run. So we want to see, and we see this even in simulations now, we have large coupling shocks. So I've tried to illustrate what we're going to try here in this schematic. We'll start with an initial single component case, say an F case, so we have just the active atmosphere. We'll take out the surface data and push that into a modified G case, I'm calling it, as the new data atmosphere, play that back on top of active ocean ice. Once that's done, we'll go and extract the SST and sea ice concentration to do a modified F case, and we'll cycle in hopes of equilibrating and minimizing the coupling shock. So to end here, a couple quick ideas on how we want to initially look at some ML and artificial intelligence. We've had some conversations on this project with SmartSim developers, which is Cray Labs, now Hewlett Packard Enterprise, and they've developed this package around Redis, which allows for an orchestrator that can enable management of ensembles on the fly. You can reach into the model and change parameters. You can reach in and look at the data as the model's running. And there are some initial results from the E3SM model here. Hopefully this works. On the mesoscale eddy front, so they have trained a network to predict eddy kinetic energy for the Gent McWilliams scheme. And you can see that we tend to get the eddy kinetic energy in all the right places, the western boundary currents along the equator, the Southern Ocean. We have pretty nice standard deviation. So it seems pretty promising, and it is also pretty robust as well. So our plan as initial proof of concept is to extend this to the submesoscales and look at ways to constrain the vertical shape function in that parameterization. I kind of said this, so I'll skip that in the interest of time. One other idea we've thought about with, in particular discussions with Steve and Bruce, is in the wave domain, it's possible we could use machine learning to better constrain where resolution is needed. So these are some diagrams of that classify the wave regime, and using a simple clustering algorithm, I forget exactly which one. And what you see, there are regions that pop out, and there are some regions that will require more spectral bins, such as this dark green down here. It has power through a number of regions. And there are some that are quite a bit simpler, say this one up here, so we could get away with fewer bins here based on this clustering. And we can think about something similar perhaps for the ocean simulations we have planned. So I think with that, I will stop and take any questions that came up.
Okay, thanks. I do not see any questions on the chat. Does anybody have any? Boy, you did such a good job, finished record time, and
Keeping it moving.
No, I have a question.
Okay.
Prerogative. So can you go back to the slide on the rapid spin up?
Yes. Here, let me pull it up. Yes.
So this is what you and I have been talking about for a long time, right?
Yes, exactly.
Okay. Has Jerry already done it?
No. From what Jerry and like Steve Yeager, the things they have done are either decadal prediction, the hindcast with data assimilation, or a long-term core, like forced dose, long-term G case are the two methods they've done.
Okay. Thanks. All right. Matt Hoffman says, what are your plans for testing and validating the new mesoscale eddy parameterization in vertical mixing schemes in polar regions?
So the first part, the mesoscale eddies, we will test against the high res where we directly resolve the mesoscales is the plan. On the vertical mixing in polar regions, what we've been doing is to validate against the ice tethered profiler data, which is a really nice data source. It has quite a bit of stuff. And we also have a partnership with the Arctic Mix folks, Jen McKinnon, who has a whole bunch of shipboard data from an early project.
Anything in the Antarctic?
No, we haven't thought about it. If you have ideas for data sources, I'd definitely be interested to hear it. I've only thought about the Arctic because of connections to interface.
Okay, yeah, maybe on the crowd team, we'll brainstorm that a bit and follow up with you.
That would be great.
Thanks, Luke.
Steve Price?
Yeah, I guess my question, I don't think it was the same question you had, but it looks to me like the target for that new spin up is just to accelerate things. Is that the idea? You're not actually trying to track observations in this case.
That's right. I would say to minimize coupling shock.
Okay. Okay. So there's no, it's not really a data assimilation kind of approach you're targeting. It's just, okay, thanks.
That's right.
No, but looking like I've talked about, we could also look at this. I think it could help be a diagnostic tool to look at where couple behaviors are that contribute to biases in the drift as well. So it's not just for spin up. I think it can be a real useful diagnostic tool.
Yeah, kind of like the Steve Klein's capped project.
Yeah, that's kind of where we started thinking about it. So
Yep.
anyway, and I should say that CAPT is doing, I don't know exactly what they're doing, but something similar. Xian is working on that, so we should talk to him about what he's doing as well. Make sure we're not both of us doing the same thing.
Right.
Shaocheng, you have a question?
Plan for tides.
I know there's a TED working group, right? With E3SM and ICOM indices people involved and some university projects by Western. I'm wondering, yeah, if you, I mean, does Ocean NGD have any plans for integrating TED into E3SM?
Yeah, we don't necessarily have a physical question yet. I've talked with Brian Arbick a little bit about possibilities that we could collaborate, but one main thrust of the NGD, in my mind at least, is to work with some of these bigger ecosystem projects to onboard those capabilities for E3SM questions. So we'll definitely be working with them. The first one we have in mind is that Arctic question, the influence of tides on Arctic sea ice loss patterns.
Okay, thanks.
All right. Thanks again, Luke. If you can kill your screen and then Andy can bring his up.
Thank you. I'm going to speak today on progress by the team working on the NGD for software and algorithms. This slide shows kind of where I see NGD software and algorithms fitting in. It's in kind of in the middle. Between on the left are the core groups. Hopefully you can see my cursor, infrastructure, performance, and the science teams that are more short-term and lower risk. And on the right are things like SciDAC and ECP that are maybe longer term and higher risk. And this kind of fits in the middle. Riffing off of Chris Golaz's talk, I think we could rename ourselves the, hey, Chris, I have this great new feature that's ready to go and you should put it in the V2 group. As we have a lot of good things going in. So I have it organized as 7 very independent tasks. So the number 1 up at the front shows I'm not talking about task 1. The first one I'm going to talk about is a new one that was just started 7 months ago, automated tuning for E3SM. So we're looking to develop optimization algorithms and software infrastructure so that we can use automated optimization and UQ algorithms to tune E3SM. So the motivation is that tuning by hand can be very time consuming and is inherently a non-reproducible exercise. And then if we have it more automated, and we can start going beyond optimal tunings to Bayesian UQ, where we have a family of calibrations that we can then propagate forward for to get the probabilities and the uncertainty propagated through our model. So the challenge is trying to develop surrogates that really match kind of the map from the tuning parameters to the metrics. You create a surrogate, and that can be very computationally expensive and time consuming. And then maybe the hardest challenge is really trying to try to quantify and write out what is the single objective function that we're really trying to minimize when we're tuning a model. and that will be necessary so that the automated algorithms can search for a minimum. So this is work that's been going on with Kenny Chowdhury and Benj Wagman, started in November. Kenny comes more from the machine learning and UQ world, Benj from the climate science world, but also with a UQ background. So really good partnership here. And so what they've done so far is really got one iteration through, well, 3/4 of this map. They've developed a problem. They're running it at the NE4 ultra low resolution so far to get all the plumbing worked out with 5 parameters. And at the top of this workflow is to do all the runs to query the model. So they've done 500 runs of a 10-year simulation, again, just NE4, doing a Latin hypercube sampling of a 5-dimensional tuning space and using the Dakota package, which is in part developed by FastMath SciDAC. They do a dimension reductions, PCA or EOF, whichever term you like, and then building the surrogates. And so they use supervised machine learning tools to build a surrogate. And through the software tools that Kenny's brought in his tool belt, they've tried neural nets, random forests, polynomial chaos, and other things. And so they've gotten this far. They haven't gone to this 4th box. I'm not sure if you can see my cursor, but calibrate and find optimal parameters. That step has not yet been done, and that requires defining an objective function that's going to be minimized. The surrogate so far does not. And I'm not sure, I'm not looking at the chat, but Kenny created a web page with about 10 or times more information than the slides I'm showing here, and hopefully he'll drop that in the chat for those that are interested. And then, so what have they learned? So the plot on the right, which I'm not quite familiar with this form of plot, but the idea is that as you have more and more training samples, the surrogate becomes better. So out of the 500 that they did, they created, they kind of experiment with grabbing different smaller sets of those, from 50 or whatever, 30 up to 500, and to see how good the surrogate matches the full data. And so the green surrogate plot is asymptoting towards the real training. So sorry, Kenny, that's as best I understand your plot so far. But you can see from this that there's 200 to 300 training cases. So 200 to 300 runs of the code is what's needed to develop a good surrogate for the 5-parameter space of tuning parameters. And so that was on NE4. So the work that Benj is about to launch now is to do the same thing for NE30 PG2 to really see how well that carries over about how many training sets are needed. And I guess if I did my back of the envelope math right, a few hundred runs of 5 years is about for NE30, it would be 1 week of chrysalis time. So significant, but not particularly daunting. So yeah, hopefully Kenny put the link in there for more information. The second topic I want to talk is work Andrew Bradley has been doing on further extensions and improvements to semi-Lagrangian transport. So I think you all know that semi-Lagrangian transport was developed under the Compose SciDAC, Pete Bausler, Andrew Bradley, Oksana Guba, and Andrew got it into V2, and that's part of why V2 is so much faster than V1. Under the NGD, Andrew extended that to GPUs. And so on the plot on the right, and I think both Mark Taylor and Peter Caldwell showed that the highlight of this, that what we're showing is simulated years per day versus the number of GPUs on Summit, going out to the full Summit machine. The black curve shows the results for the die-core dynamics plus 10 tracers for the NGGPS benchmark, and we had 0.97 simulated years per day. Now that Andrew's switched the transport over to semi-Lagrangian with GPUs, that jumps up 40% throughput increase to 1.38 simulated years per day. And then interestingly enough, that benchmark had 10 tracers, but I know 40 is kind of a more typical E3SM number. So going from 10 to 40, with semi-Lagrangian tracers, it only drops 10%. You're still getting 1.24 simulated years per day, while back with Eulerian, you really took a huge hit. So not only is it fast, it's much more scalable. So you climate scientists now have the choice of running your code super fast, or you can slow it down again by throwing in dozens or even small hundreds of tracers and still get good throughput. Something Andrew's doing that this is not funded by NGD, but it's closely related is looking at super resolved tracers. And so right now in V2, we have a physics grid and a dynamics grid, and the tracers are on the same dynamics grid, but he's freed it up so tracers can actually be on their own grid. So in V1, we had one grid, everything was NP4. In V2, we had two grids, NP4, PG2. And so now potentially, if this is adopted in version 3, we could have 3 grids, physics grid, dynamics grid, and a separate tracer grid. And so if you look at the schematics on the left, this is on the top is the green points are NP4 and the red boxes are in PG2. That's how version 2 is running. But the bottom box is a picture where you could do NP4, the black dots for dynamics, PG6, the green boxes for physics, and NP8 for tracers, the red dots. So why would you want to do this? Well, if you really want to know the filament structures of plumes for aerosols or other really high resolution data with tracers where you can preserve sharp interfaces, you will have this flexibility. And then the verification proof of this is the 3 plots. On the left is the initial condition and also the analytic final solution where you have a tracer with a value of 1 where it's orange and 0 where it's blue, or purple, whatever that is. And if you go through one cycle where it should return exactly where it is with a non-diffusive solver, for the top you get the NP4 where it's diffused out, but if you do the NP12 for tracers, you get the really nice picture on the bottom. And this is both cases are with NP4 dynamics, just higher tracers. So the third topic I want to talk about is the great work by Hyun Kang. The first one is on the work that we've talked about before, but is really getting finalized and into the code, is on the barotropic mode solver. So the current ocean solve is explicit subcycling for the barotropic mode, which takes about 60 halo exchanges. So those are local MPI communications to do the split explicit. But if instead we can step over that with an implicit solver, we can win if we can take much fewer than 60 communication steps to do that one implicit step. And so on the plot on the right, we show MPass Ocean, 18:6 grid, up to 32,000 cores. So this is real. The explicit subcycling in the blue, we get Hyun gets a 1.74x speed up for the full ocean, dynamics, from the blue curve down to the red curve with this split explicit. He's also been looking at using Trilinos linear solvers, the black curve, and while they're competitive at the lower processor ranks, they are not at the top. But they're still we're keeping those around because that might we'd be able to leverage all the work Trilinos team has done on getting things on GPUs and maybe have a quicker path to GPUs there. But the other work Hyun is doing in this area is starting to directly put OpenACC directives in to parallelize his code, to get his code running on GPUs as well. The more recent work that Hyun is doing is in the baroclinic time stepping, and Luke referred to this as a possible area of research. So the current step is a 2-step predictor corrector to get second order. So Hyun looked at Adams-Bashforth, where you can do a single step to get second order. So potential of a 2x speed up. What he's found, and I think was not unexpected, is that it's a less stable approach. So he had to decrease the time step, but not by a factor of 2. So the picture at the right shows that by dropping the time step from 360 seconds for the 2-step predictor corrector method to 300 seconds for a 1-step method, he gets another 1.6 speed up for the full ocean dynamics. So this is kind of work in progress, and it still needs full validation, but you can see from the plots that he's pushing that, and is in communication with Phil and Luke and Mark in past world. Moving on, the fourth task I want to talk about is continuing work from Salil, Mahajan, and now with Michael Kelleher on the climate reproducibility. And so this is the work that's on how to diagnose if a non-bit for bit change is climate changing or not. This is, of course, very challenging because of the chaotic dynamics of climate. And so what they've done and this is work in the ocean on this slide, of looked at how they can change parameters such as the Kent McFarlane McWilliams parameter kappa, and you know, you can, in the plots up there, you can see it's a change from 1800 to 600, so it's a huge change, and you can see the ensembles diverge. But with their test, they can detect a change of that parameter from 1800 to 1799 with a 30-member ensemble. If you look at the plot on the lower right, if the ensemble size gets up to 60, which is more expensive, but they can start to detect changes with high confidence that are even, you know, 0.001% of that parameter. So so this is, you know, the idea is that that round off changes will be, you know, due to order of operations, your code will be lower than this, and we'll say they're the same climate, but large changes in your code, bugs you put in that are on the order of changing a parameter, a small percentage will be caught. And then the second slide on this work, they're now working on getting this in the single column model for the atmosphere, you know, or have all the infrastructure in place to perturb the ensembles, to hook up the multivariate testing framework, and to detect changes in the different atmosphere physics. And then on the right is something that we're all looking forward to, and I saw some excitement from Rob when this was finalized a few weeks ago, the infrastructure team, that we now have these reproducibility tests that had fallen into disrepair now back on. I believe this is Michael's work, thank you. And he made changes to adapt to the names, to get the multivariate KS tests and the time step convergence tests now running in there. And so anyway, we're excited that that's in there and continues to be deployed in the infrastructure. The fifth topic is one slide on work that Andrew Steyer did with our year-round intern Cassidy Krause, who, good for her but bad for us, has decided to become Professor Krause and not come to Sandia as a staff. But so so the two of them worked on exponential time differencing methods in the non-hydrostatic atmosphere. So as we switched from hydrostatic to non-hydrostatic, we've had to do a Newton solve in the vertical coordinate. So that's the IMEX methods, but ETD methods are another option. The plot on the left shows a whole zoo of different ETD methods that they developed compared to the IMEX method, which is in the code. I bolded the IMEX so you can see. This is error versus runtime. So these are both outputs of the model. You want short runtime and small error. So you have a kind of a Pareto front, a choice to choose. And you can see that the IMEX is good for a lot of that, but some of the ETD, this red curve is getting competitive. The curve on the right is the same run, but strong scaling out. So there's only 6 elements per core instead of 18. And you can see most of the curves stay about the same, but the IMEX one slows down relatively. And kind of the issue is here, and you know, the possibility with the ETD methods is that they are more scalable. And so even this one data point from the left to the right shows that the ETD methods are now, you know, the lowest error for a given runtime and are looking competitive with the ETD, with the IMEX method. The IMEX method is the one that's in V2 of the model. This is another work is going on joint with Julian and Vijay at Argonne with Karen Devine from the Fast Math Institute on using Zoltan to look at improving the partitionings and the weight generation. So they're working on generating the weights in the coupler matrix, which for typically, or the most prominent is the ocean atmosphere coupling, with have of course very different grids, the spectral element and the MPAS Voronoi grid. And so they've worked on two related efforts. One is doing it offline, where you pre-compute the mappings and the weights using MB Tempest, which is a combination of MOAB mesh code and Tempest remap, and then an online one, E3SM MOAB, where you can generate the coupler weights and mappings on the fly with every run. So in both cases, they're working on parallelizing this to speed it up and to make it scalable in memory. And one thing that they've done with a capability that they've added, that was improved and added, I think in Zoltan, is to instead of having a smart partition for the atmosphere across the processors and a different one for the ocean, which is currently done, they each have their own way of doing it, is to first do the ocean partition and then let the atmosphere infer its partition from the ocean, so that the communication is largely local. So the plots in the upper right show that, and you can see the ocean and atmosphere color schemes for their partitionings are almost a dead match, meaning that those will not need MPI communications, but will be local for the atmosphere and ocean to talk. And they're doing that offline and doing that online as well, like I said, so that it can be done on the fly with any number of any PE layout you grab. You can just do this on the fly. And then the final topic I want to talk is work going on at UT Knoxville, Tennessee. Professor Josh Hu and grad student Rongyu Chen on nonlinear solvers for the atmosphere chemistry. They've been working on the two-stage Rosenbrock solver and hooking it up to both the UCI chemistry package and the TropeStrat Mozart MAM7 chemistry package. And they found that it's second order convergence instead of the first order of the current implicit method. IMP is the acronym for the current implicit method. And some of the plots show the same, that much better order of convergence with iteration. And in their tests, in a box model that runs all this, they've got a 20 and 25% speed up due to the improved solver. And they're working on implementing an E3SM. I think they have it in there working, but not quite verified or as performant as they thought yet. So they still have some work to do, but they're definitely in there getting this into E3SM. And also on their work, they've done some model evaluation, looking at changing the time step from 1800 seconds to 180 seconds and seeing some of the results. But I'm not particularly qualified to speak on this. So those are all the tasks that are going on in NGD. You can tell they're independent. There's lots of good work to speed up the code and improve the infrastructure. Been dreaming and trying to keep this list active of all the things we might want to fund in the future. I kind of use a greedy algorithm of low-hanging fruit to what we can fund and what we can, and usually staff and fund. So here's kind of a laundry list. Not all this would be under software and algorithms, NGD. Some of it's with Scream or Ocean, things like that. But continue with automated tuning, really double down on verification and correctness, such as convergence in vertical dimension and time, rigorous energy conservation, optimal vertical coordinate, adaptive time stepping. We have different time steps for different RRM regions, high order TRISC for ocean, improving sea ice speed, machine learning, low hanging fruit, really developing the infrastructure for large ensembles where, I mean, as I was showing in the first anecdote of the Latin hypercube sampling for a 5-member parameter space, we were already up to hundreds, so we could easily get up to wanting to do thousands of concurrent runs and improving spin up. So anyway, I'll stop there and take any questions. I've not been monitoring the chat.
Okay, trying to Lots of discussion on the chat line. So Kenny, you were first, just as a comment, with anything more than just the link to the circuit model.
Oh, yeah, I just wanted to answer briefly one point that Surat had mentioned. What have we learned from the ultra low resolution model that maybe we can take to the high resolution model? And it was interesting actually that, so we had this 500 simulation run, simulations that we tried on E3SM with the NE4 model. And we tried different simulation lengths, 2, 4, 6, 8, and 10. And the 10-year simulation length run with 500 training points did the best. That was the most, right? That had the most signal to noise ratio, the most training data. But almost equivalently, we could have gotten away with a 6-year simulation run and 200 to 300 points. So there's some savings there. There's some redundancy. We didn't need all that training data. So that's kind of where we're going into it for the higher resolution runs. Now we won't know exactly how many we'll need for the higher resolution runs, but what we can do is we can spend a week doing 100 runs and see if we need more, and then we can incrementally increase the number of runs given how good our circuit model is.
Okay.
So yeah, I just wanted to answer that.
Sarah?
Yeah, so my question centers around, I mean, they got to some of it, but I still wonder if the auto tuning sort of methodology might be too expensive for the large model. If we need to, I presume we will, given the number of uncertain parameters we want to explore, and there will still be a need for expert auto tuning sort of input. So not expert tuning input rather than fully automated, but that's a philosophical thought. So
yeah, go ahead.
I just quick point. I don't see it as necessarily we're trying to replace everything. This is just sort of trying to augment or help in certain areas. So, but I think those are excellent points, and absolutely, there'll be areas where the machine learning tools are just not going to be adequate.
Yeah, and I was going to say, I think it's expanding the toolbox, so it's still, we use, expert judgment in humans and interpreting the bugs. A lot of the, I know the tuning work is actually finding bugs and not just finding parameters. But if you can kind of up the tool sets, you can push a button and do a whole run, a whole parameter sweep, and a whole calibration. Even just one or small parameters or just the atmosphere. If that's kind of more the granularity of the calibration process. And I think there's also, this research area is so open-ended. There's multi-fidelity methods where you can start learning from NE4 to start your knowledge for NE30 and use your NE30 to surrogates to guide your tuning of NE120 and things like that. I think that's a very wide open research area.
Okay. Tang?
I was wondering what the additional computational cost will be adding the tracer grid. So I personally will be very interested to seeing the results of the fine resolution for the chemical tracers.
Andrew, do you want to take this one?
Sure, thanks. Yeah, good question, Chi. I answered in text with some details, but I'll emphasize one part of that. So one of the things that we think about for using GPUs effectively is having the kind of work that spreads out well. So in particular, what we like is something that can increase the quality of the model without increasing the number of communication rounds per unit of simulated time. So this is sort of a perfect example of that, where the particular case that Andy showed on the slide was NP12 tracers. So that would increase the overall cost of tracer transport given the same resources by a factor of 5, back to about what the original Eulerian transport cost, but with about an 8x greater resolution. But that factor of 5 is the best sort, for GPUs or anything like it because the communication rounds stay exactly the same with an increase in communication volume in 2 out of the 5 rounds. So that could be easily fixed just by increasing the number of GPUs you use for that particular run. So this would be in contrast to something that, as you increase the resolution, also requires a smaller time step.
Walter Hanna.
Yeah, so it mostly answered in the chat. I was just kind of wondering about the auto tuning without having an objective function defined. It seems like that's kind of backwards. Like you should go in with, even if it's a preliminary idea of what you're tuning to, and that could guide how you build the tool, rather than building a tool that can do anything and trying to back out what the objective function should be. So I don't know. I just wanted to get thoughts on that. I know there's no right or wrong answer, and Benj and Ruby chimed in, but Andy, if you have any thoughts, I'd be curious to hear them.
Yeah, well, so I think there's different surrogates you can imagine, and you can have surrogates for your metrics or surrogates for your primitive variables. And I think if you do surrogates for your primitive variables based on the EOF vectors, then I think you can do that before you define an objective function. But I think you could also think of the parameter versus objective function map and develop a surrogate for that, and then you would need it. Yeah, if you're going to do tuning, then you do need an objective function to go downhill. I don't know, Kenny, do you want to fix what I just said?
No, that's a great point. I think one thing that I think this is a really interesting point. So, our philosophy is that let's create a surrogate for the training data first, and then that's independent of the objective function. And then whatever objective function that needs that particular quantity of interest, we can just plug that in. But it could be that it's just too generic and it doesn't work like that. And but the good news is that the way we're creating the surrogate, we're trying to do it in a robust way, and we're not trying to use overly complex models, so that if we need to change the surrogate model on the fly, we can do it, and we're not sitting there trying to tune it for a week or 2 weeks or something like that. So we're trying to balance this idea of complexity and accuracy for the surrogate. And so, yeah.
So actually, on that point, I think something I missed was how complex the surrogates are. Because I mean, if you were let's say you only wanted to tune the global mean variables, like you had precip and top of atmosphere energy balance, then it seems like you could make the surrogates much simpler, and maybe you only need like your simulations. And so if you started out with that objective function, then you could really simplify everything else.
Yeah,
But it's
we can do that.
surrogate models actually predicting like spatial patterns.
Yeah, so that's what we're doing.
If you predict the full fields,
it seems more complicated than it needs to be for a first step of an auto tuning thing.
We think it could also be robust for different applications and different choices about how to tune the model and what to prioritize. So we think that's a good reason to do it this way, and it does then allow us to test our metrics very, very quickly. And once we have the surrogate, and we expect that to be a really challenging part of this. And we don't really know what metrics are going to perform best until we have a way to test it. So that's part of the justification too.
And then one last point too is that we can do both. I mean, we're using the same tools to do both, and the software we have can easily switch between the two. So, yeah, in some cases, maybe we just want to predict a single scalar mean quantity. And in some cases, maybe we want the whole spatial varying field. We can do both.
Okay, thanks.
Ruby, like you're next.
Yeah, so I think my question is partially answered already. I was also wondering how complicated the surrogate model currently built are, whether it is like one surrogate model per target variable, and whether there is a benefit of building a surrogate model for multiple target variables at the same time where you account for the covariability among the target variables. But that become a very high dimensional surrogate model, may be difficult to build.
Yeah. So I'll answer it quickly, but in the link, I'll put the link again, but if you scroll up, it's a little bit more thorough explanation of what the surrogate is. But so we're not trying to create a surrogate for every single latitude, longitude grid point. We do a dimension reduction on that spatial field, and then we project it onto a lower dimensional space, and then fit that lower dimensional space. So we're only creating maybe 8 or 10 or less than 20 different surrogates. But the models themselves they take fractions of a second to run, and to train it's on the order of seconds, so it's not overly complex, and we're using very robust, very ubiquitous tools like PCA. We're not and typically we're not using things that need tons of tuning and things like that to create those models. So but of course we can get very complex in terms of the modeling, but then we spend too much time doing that.
And right now, each field is reduced by PCA independently, but we definitely want to try, because the fields are going to be so correlated,
Right, exactly.
combining them into one huge vector and then doing the dimension reduction on that, and then predicting the coefficients on that combined multi-field vector.
Yeah, great, thanks. It's really good to see the progress.
Thank you.
Okay, with that, Shaocheng, you can bring your screen back and I'll turn it over to you.
Okay, so I will give an update on the E3SM next generation development atmospheric physics. So this work is really being done through a very close collaborations between the DOE lab scientists and also our collaborators from the universities, as I'm showing on this first slide. Different from the screen project like Peter described last week, this NGD project is targeting to particular for the E3SM V3 with a resolution that still need deep convection and other complicated atmospheric physics for different E3SM applications. So the current effort is really emphasized on two parts. One is try to reduce the outstanding bias we found in E3SM V1. Particularly the bias in simulation of cloud and the precipitation. We also see the too strong aerosol indirect forcing in V1. We want to improve that. And also we have very poor scale awareness when we increase the model resolution. So this is another thing we are targeting to. The second emphasis would be to enhance the model capabilities for coupling across the Earth system. So like we are currently lacking the interactive atmospheric chemistry in V1 and also missing some critical physics for aerosol species. So we would like to improve the representation of aerosol and atmospheric chemistry for coupling across different Earth systems. So the development will address the combined problem of scientific accuracy, scale awareness, and also computational efficiency. So this slide gave you a quick overview about what we are doing now. Like most of the model bias in V1 are highly relevant to the current representation of deep convection and also clouds. So one big effort we are making is try to improve the representation of cloud and the convection currently used in V1, like those are the parameterizations used in current V1. We have several efforts in parallel to improve the deep convection, such as we are testing two unified scheme, club cells and EDMF, for a unified treatment of turbulence, shallow convection, and deep convection. We also continue to improve the deep convection scheme used in current V1, the CM scheme, by adding a lot of enhancement. I'm going to show later. We also use the P3 to replace the current MG2 in order to improve the description of ice cloud and also the aerosol cloud interaction. To improve the model capabilities, we are working on implementing like the new aerosols new aerosol physics that are critical to better disperse like the nitrogen aerosol, second organic aerosol, stratospheric sulfate, and the dust. We also implement the UCI chemistry. This is the interactive chemistry that will play a central piece for coupling aerosol chemistry and the BGC. Model integration and evaluation and also tuning is another big part for this project, particularly at this stage, because most of the new features are already in E3SM. It's time for us to think about how to put things together for tuning and evaluation. So I'm going to show some notable progress in the next few slides. First, the contributions to the E3SM V2. Chris Gallas showed some, update on E3SM V2 development. We also delivered a few new features developed at the earlier stage of this project to the water cycle group for testing for V2. That include an improved convective trigger for better cycle precipitation. Like showed in Chris' talk, the V2 cycle precipitation has been largely improved compared to V1. So I believe this is mainly coming from this improved new trigger we developed in this NGD. We also developed and retuned the convective gravitative wave parameterizations for a better QBO. This retuned parameters has been also implemented in V2. In addition to that, we also provide an improved dust emission scheme and also an updated club. So the progress on convection and cloud parameterizations. So like I mentioned, we have several efforts try to improving the current deep convection. Then, like I showed at our last fall meeting, we have implemented a stochastic convection scheme and also add the mesoscale heating on top of the ZM. Both implementation has led to an improved like the precipitation intensity distribution, like showed in this figure, which lead to less light rain and more heavy rain, bringing the simulation closer to the observations. By adding the mesoscale heating, we get a clear improvement in the carbon wave and also the MGO, those tropical variabilities. In addition to that, we recently implement a more sophisticated cloud microphysics for convective cloud. By doing that, like shown in this figure, this is a 5-year DGF precipitation simulated by the default model. This is the V2 model and plus the new cloud microphysics for stratiform cloud, like the P3. This figure shows the model with the new convective microphysics. You can see that the white bars over the SPCD has been reduced by using the new cloud microphysics for convective cloud. We also get improved simulations for over the Amazon region, like see we produce more precipitation compared to V2. We know V2 already reduced the dry bars over this region. This feature is getting better by using the convective cloud microphysics. Another thing we found actually by using the new cloud microphysics for deep convection, you can see you get very nice simulations of MGO and carbon wave by compared to the trim observations. We also make a lot of good progress in making club for deep convection. As you know, club right now is used for turbulence and shallow convection. So Vince Larson's group has made some nice progress making club for deep. It's called club sales. Here is the figure shows the cloud fraction average over the DGF, over the warm pool region. Those means the cloud are mainly relevant to deep convection. The black line is the observation. The blue line is from V1 model, and the green line is the club sales with the deep convection turned off. You can see that club sales can well capture the deep convective cloud over this region. One group also made some other improvement, such as they implemented turbulent damping time scale to improve the distribution of shallow cumulus and the near coastal stratocumulus. You can see this is the default model, this is the new model. We definitely see clear improvement, for the stratocumulus along the coast. So for the EDMF, the Joel's group is also making some good progress on that. They have successfully implemented EDMF in screen by coupling EDMF with SHAC. So this figure shows a result from their initial run, like the 1 year climate simulations. This is the SHAC plus ZM. Both runs are for resolution at 1 degree. So you need to turn on the deep convection scheme. This is, but the different from the default screen, in this run, they use MG2 microphysics. This one is they turn off the ZM by using the SHAC plus the mass flux. This is the coupling the mass flux part with the turbulence and shallow convection scheme used in screen. So you can see that, but one thing I would like to mention that actually the SHAC plus ZM, they only implement non-precipitating plumes for the coupling. And so all the precipitation is not from convection, actually from the MG2, the cloud microphysics. A quick look of the result, you can see the precipitation is significantly improved, but a nice feature is the double ITCZ is largely removed. That's definitely indicating the convection play a major role in producing the double ITCZ. Definitely there are a lot of work need to do in order to make EDMF for better simulate the mean precipitation field and maybe other things we have not seen. So for the cloud microphysics, Jiwen's team has made a very good progress in that, in implementing the P3 into the E3SM V2, the atmospheric model V2. I really appreciate their effort. Actually, the P3 plus V2 will be used as a code base for our ongoing convection assessment test. So I only gave them a very short time period for getting P3 done in E3SM V2. They really worked hard and make that happen. I really appreciate the effort from Kobe, from Jiwen and Kai. And there are some interesting features we found after we implement P3 in V2. One is we see an improved simulation of ice cloud between 50 south and 50 north. Like I showed here, the blue line is the default model from MG2, the red line is from P3. Compared to observation, you see some improvements here. And also we found the P3 can also improve the frequency of heavy precipitation rate over the corners regions. You also see some improvement, for the cloud radiative forcing over the polar regions on both hemispheres. But big surprise for us is after we implement P3 in V2, we found the E3SM show more scale awareness scale. The figure showing here is the first row is the NE120. This is the quarter degree simulations. This is the 1 degree simulations. Here is the difference between these two simulations. This the left column shows the default V2. That means using MG2, and this one is using P3 to replace MG2. You can see that after using the P3, if you look at the difference, the change in annual mean precipitation from 1 degree to quarter degree is significantly smaller in V2 with P3 than the default V2. So that does show some better scale awareness, scale across different scales. Anyway, so we also made some good progress atmospheric chemistry and the aerosol physics. So the chemistry team has successfully implemented the UCI chemistry in E3SM. This figure shows actually the E3SM. UCI chemistry can reasonably simulate the total column ozone by comparing with the satellite data. It's pretty nice. They show very nice seasonal variability also. So this team also worked very hard to try to make sure their development can meet the requirement from the BGC. Like they already make the UCI chemistry and the linear ozone V3 code ready well before their original plan. So those code is ready for the BGC simulations, like coupled methane ozone vegetation simulations. They work very closely with the BGC group. Also good progress making from the aerosol physics from Hailong's task team, and we already implement a lot of improvement of for better representation of the natural aerosol, solid organic aerosol, stratospheric, sulfate, and also dust in E3SM. In addition to that, they also implement advanced aerosol module Mosaic to help coupling the M4 and also 4 gas chemistry to support the aerosol development. So for moving forward, our current main focus is try to make sure all the different new features can work together well as what we expect. So there are a couple major activities that are being conducted by this group. One is, to select a suitable convection scheme for V3. As I mentioned, we have several major efforts try to test in different candidate scheme for V3 convection scheme. Right now, we have just launched a major simulation campaign for the convection assessment. So this assessment will divide it in 2 phases. One is the phase 1, which was just completed. The phase 1 is mainly to give the opportunity for the model developers to testing their new features with the new code base is the V2 plus P3, and also provide some insight about what their new features performs. Our really assessment will start for phase 2. That will include more thorough tested for the evaluation, and so the result from the phase 2 will be used for making the decision. All the developers team has a couple weeks to digest what they have learned from the phase 1. Then probably they need to retune some of the parameters in those new features in order to be ready for phase 2. Phase 2 will be the assessment we used for the selection. Another effort is we work very closely with the BGC group, try to make sure our development in chemistry and aerosol can meet the BGC science field science simulation campaign need. So we work very closely with them. Like I said, the chemistry would be a central piece for coupling aerosol chemistry and the BGC. At this moment, so it's time for us to think about integrating different new features and start the model tuning and the evaluation. So we have a big evaluation team. They are also start to create a conference page that can provide a common testing framework for all the individual development teams, so we can define the standardized experiments for testing all the new features. So there are a lot of activity that are being conducted by the evaluation team. So in summary, this NGD project was created specifically to address the model bias and enhance model capabilities for V3, but some of the new features could be further integrated into the V4 atmosphere model, which is a Scrum code base with other necessary physics developed from this NGD and other E3SM modeling projects for different E3SM applications, as clarified by Dave last week. I also want to see this NGD represent a close collaborations with the DOE-funded other modeling project. So actually, there are several new parameters that are being implemented in E3SM developed from our university collaborators. The development are on track. We have seen some encouraging results in reducing the bias in cloud and precipitation. We also see some indication the new model may show better scale awareness. And we already add some new aerosol and interactive chemistry for better coupling across different Earth systems. Okay, I would like to stop here to see if there are any questions from the audience.
Zhijing said, good clarification on the Screen V4. And thank you for working with the ESMD project. Walter has a question.
Yeah, so the scale awareness thing, I think I've had this conversation with many people here, and I'm starting to really hate this term because it's so, it doesn't have a definition that we can quantify. And so I'm surprised that you mentioned this qualitative thing that it's getting better, even though we can't know that, right? So I'm wondering if anyone else is thinking about ways to quantify that, maybe with horizontal resolution convergence tests or some other fancy metric.
Yeah, Walter, you are right. Actually, my statement is just based on what I observed. In the V1, we know when we increase the model resolution to a quarter degree, there is significant, changes in precipitation and also the global radiation budget. We need to retune the model, but with P3, we found actually the change is much smaller, and also the redstone is also does not change much. We feel that also means we don't need to significantly tune the model when we increase the model resolution. But
yeah,
we don't have a strict definition for how to judge the scale awareness.
It seems like another interpretation of that, a more pessimistic one, would be that the biases are just more stubborn when you switch to P3, right? It's not necessarily that they're better because they're not changing.
You can see in this way too, but it's closer, it's smaller than the MD2, the default V2, and the simulation is better by comparing with observations. So you can think in another way, I think.
Okay. Hugh Morrison.
I don't know if people can hear me very well. I don't have
Yes, I can.
great audio here. Can you hear? Okay. So I typed this in chat, but I'll just ask it, I guess. And this is on the theme of the so-called scale awareness. Do you have any idea why the P3 seems to have that? It's definitely not a result I would necessarily expected compared with MG2.
Yeah, so one idea we had is in the MG2, a lot of things relevant to ice microphysics. We use a lot of parameters arbitrary to separate the ice categories. So, but those type of things actually is more physically represented by P3, we have less parameters. That probably can help reduce the sensitivity of model to resolution change, because a lot of parameters need to tune the particular for one particular resolution we used. So if the representative is more physically represent without using too many parameters, that will help to improve the cloud, like the scale awareness. So this is one thing we were thinking about. Maybe Jiwen can, share some of her thoughts on this.
Okay. Yeah, I think with P3, we do have nice tunable parameters. For example, the S effector radius and S force speed, and also other less tunable parameters. Basically, I think the more physical, usually more physically representation of the physical processes would have less scale sensitivity. So I think those the aspect we'll think of. Probably there are other things. We just need to look into more on that.
Okay, thanks. Yeah, that makes sense. That what you're saying with less parameters and stuff. It's just actually seeing that, I guess, in practice is not necessarily I would have expected it. So, but thanks for clarifying.
Yeah, it's also a surprise to us too. Yeah.
Okay.
Hey, Shaocheng, I actually have another question. I can type it in the chat if you need, but
okay, go ahead, Walter.
Go ahead.
I'm curious about, since we've been planning this this bake-off between the different convection scheme configurations for a while. I'm curious if you guys have nailed down what things you're going to compare. Like, what are your key metrics? Are those clearly defined yet?
Yeah, actually, I formed the informal advisory committee for helping me, to make sure the comparison are fair and also thorough. We have identified the so-called top 10 metrics that, probably is not surprise to most of you, will be relevant to cloud precipitation, because those are the things the convection scheme is supposed to do, right, to improve the simulation of cloud precipitation. And we also include, the metrics for the aerosol cloud interaction. And also would like to look at, the climate sensitivities by replacing the old scheme with a new scheme. There are, several experiments we designed, particular to, to get those goals. We also look at the scale awareness like this in our future. I believe, E3SM will run with across different resolutions. We need the model have good scale awareness, then we don't need to dramatically retune the model whenever we change the model resolutions. So those are the top metrics we are going to use. We also discuss with the developers in order to address their concern regarding, things they care. But overall, we have identified the top 10 metrics. We are also going to look at, the E3SM diagnostics, AMWG diagnostics, the variability diagnostics, and also the ARM diagnostics. So all things combined, but we do need to emphasize on things relevant to convection, that particularly is cloud precipitation, aerosol cloud interaction.
Okay. I think that's the end of the questions. Shaocheng, thank you very much. Thank you, everybody, for calling in. Tomorrow, we will have the final two talks in this series from Kate Calvin and Ben Von Lamberty, starting at 8 Pacific, 9 Mountain, 10 Central, and 11 Eastern time. So we'll see you all tomorrow, and thank you for tuning in today.